Hey y'all, it's Mrs. Blasky. Today we are going to talk about periodic trends. This is a big topic in AP Chemistry. It is a question that comes up all the time, and it's something that requires a lot of explanation. This is always one of those defend your answer, justify your answer kind of sections. So we've got a couple main periodic trends that we're going to talk about. We're going to talk about atomic radius, we're going to talk about ionization energy, and we're going to talk about electronegativity. So first off, we'll talk about atomic radius. In first year chem, we basically asked you to memorize the pattern. So we asked you to know that atoms increase in size as you move down a group because you're getting more and more energy levels, so that atom is getting larger and larger as it holds more and more electrons, and moving across a period from left to right, the size decreased. And that was sort of unusual. You would feel like decreasing that direction is a little strange. Feel like it should get bigger as you have more protons, as the atom gets larger. But really what's happening inside of that atom is very different. When we add more electrons as we go across a period, even though we are adding those electrons to the atom, those electrons are all filling in the same energy level. So that energy level has a specific size. And as you fill it with more electrons, it has the space already to fill them. It's sort of the idea of if you have a bunch of people over to your house doesn't expand to fit those people. They just find room inside of the house. So even though those electrons are filling that energy level, the number of protons is also increasing in the nucleus. So we need to talk about something called the effective nuclear charge. So as those protons enter the nucleus and increase the positive charge of that nucleus, that positive charge of the nucleus is able to exert more force on the negative electrons on the outside, pulling those electrons in closer and closer to the nucleus. So that actually decreases the size of our atom as we add more protons. This goes back to that idea of Coulombic attraction and Coulomb's law. So by increasing the number of positive charges in our nucleus, we are creating more Coulombic force or increasing the Coulombic attraction between the nucleus and those electrons. So when we talk about effective nuclear charge, we're really talking about the ratio between the positive charge in the nucleus and the negative charge of the electrons around the atom. So we can use this idea of effective nuclear charge to talk about how the size of an atom versus the size of an ion can be determined. So when we're talking about positive ions, when we're talking about something like lithium going to lithium plus, notice that from this data, we can see that lithium as a neutral atom is much larger than lithium as an ion. And when lithium loses an electron, that outermost valence electron that it loses is in the 2s sublevel. So when it loses that electron, that 2s sublevel is now empty, meaning that the closest energy level to the nucleus is now the 1s. Because that 2s is no longer occupied, 1s is the level we're looking at, that automatically makes the atom smaller. But also by losing that electron, you're increasing the ratio of positive charges to negative charges. So that nucleus has a larger effective nuclear charge now than it did in the neutral atom. And so it's able to pull that 1s sublevel even closer to the nucleus than it could in neutral lithium. The opposite occurs for negative ions. A negative ion is larger than its neutral atom. By adding that extra electron, you are decreasing the effective nuclear charge. You now have more negative charges and less positive charges. And that decrease in the effective nuclear charge decreases the Coulombic attraction between the positive nucleus and those negative electrons. So that atom, the neutral atom is smaller, the negative ion or the anion is actually larger because that nucleus doesn't have as much force to be able to exert on those electrons, it's not able to pull them in as tightly. We can also talk about ionization energy. The ionization energy is the energy required to remove an electron from an atom. Ionization energy, like we talked about in Gen Chem, requires more energy when we go to the right across a group, and it requires less energy as we move down a group. Again, we can base all of these patterns on which energy level those outermost electrons are in, those valence electrons, and that attraction between the nucleus and those electrons. So when we are talking about removing an electron, the distance between the electrons and the nucleus is decreased. But as we go down a group, we already have more and more energy levels as we go down a group. So if I'm removing an electron from a larger energy level, those electrons already are not as attracted to the nucleus because of that distance between the nucleus and the electrons, so they do not require as much energy to remove. If I have an energy level that is closer to the nucleus, that is going to require more energy to remove. We can also talk about as we go across a period, this is the same idea of that effective nuclear charge. Because of the larger nuclear charge in the nucleus, because of those protons, they are going to exert a larger force on those electrons, holding onto those electrons tighter. So if we either increase the charge of the nucleus or we decrease the distance between those electrons and that nucleus, those are two different ways that we can affect that Coulombic force or that Coulombic attraction between those. We can also talk about multiple ionization energies. So we will talk about first ionization energy, second ionization energy, third ionization energy. And those involve removing more than one electron. So first ionization energy is removing the first electron from the atom. The second ionization energy is removing a second electron after one has already been removed. Now, every time we remove an electron from an atom, it is going to require more and more energy as that the effective nuclear charge is increasing and that Coulombic attraction is increasing. It's always going to require more and more energy as each electron is removed. But we can see some patterns in those ionization energies. We can see these large jumps between one ionization energy and another. Now those largest jumps, so here we went up by a factor of 10. Here we go up by a factor of not quite 10. Here we go up by a factor of 4. Those largest jumps show us when we are starting to try and remove an electron from the next closest energy level to the nucleus. So if we think about sodium, sodium is a 3s1 element. So its first electron that gets removed is from the 3s sublevel. When I want to remove a second electron from sodium, now I'm trying to remove an electron from the 2p sublevel. That 2p sublevel is closer to the nucleus, so it is going to require a lot more energy to remove than a 3s electron. Again, we can see that pattern as it goes across all of these beginning first or third energy level elements. We can see that as you remove those electrons, where that biggest jump is where we change from removing from the outermost energy level to the next closest energy level. We will talk about this pattern a lot in class. We can also see there is some variation in those. There's some exceptions to the rule, but we are not going to concern ourselves so much with those exceptions to the rule. The last periodic trend that we're going to talk about is about electronegativity. Electronegativity measures the attraction that an atom has for electrons to form a chemical bond. We talk about electronegativity a lot when we're determining the difference between polar and nonpolar bonds. We're talking about electronegativity differences when we're talking about the difference in ionic versus covalent bonds. Fluorine on the periodic table has the highest electronegativity. It's on a made-up scale. It doesn't really have a unit or mean anything. Fluorine has an electronegativity of 4. The noble gases, we do not talk about electronegativity for gases since they already have their full octet and their full energy level. They're not really going to be attracted to gaining more electrons, even though they can form bonds. Elements that have high ionization energy are also going to have high electronegativity because their nucleus is so strongly trying to attract those electrons. Those both both those measurements, electronegativity and ionization energy, both talk about how tightly those electrons are held or desired by that nucleus. So we've got the general trends here. Again, remember, in AP chemistry, just saying, well, because this atom is below the other atom on the periodic table, or this one is farther to the right or to the left, is why this pattern exists, is not enough. We need to explain what's going on in the structure of the atom between the forces acting on the nucleus to the electrons. Excuse me. That's enough for today. I'll talk to you later. Bye.